Alright, today we are going to start our unit on graph theory. So I'm going to give you a little bit of background and introduce you to some of the basic vocabulary. So, the birth of graph theory goes back to the mathematician Leonard Euler, who was a mathematician in the 1700s, and in 1736 he went through the town of Königsberg, Russia. Königsberg is divided by a river into 4 separate sections, and the sections are connected by 7 bridges. The question that the town wanted answered was, is it possible for a person to take a walk around town and cross each of the 7 bridges exactly once? So, while that might seem like a silly little problem, graph theory actually has a lot of applications, including finding efficient routes for Amazon deliveries, police patrol, garbage collection, mail deliveries, any type of delivery. Those are considered types of management science problems, and a lot of basic things about graph theory can help us solve these problems. They are typically considered Euler path or Euler circuit problems, which we'll get to in a future video. Today we're just going to take a look at some of the basic vocabulary. So, 4 Euler circuit problems. Our first bullet point here is, what is a routing problem? These are problems concerned with finding ways to route the delivery of goods and services to an assortment of destinations. Okay, so this includes packages, mail, newspaper, pizzas, garbage collection, bus services, etc., and trying to find efficient routes for all of these. The destinations could be houses, warehouses, distribution centers, terminals, etc. So, in general, we have 2 questions to answer when we're looking at these type of problems. The first is the existence question. So, first of all, is an actual route possible? So, is it possible to cross all 7 bridges in Königsberg exactly once? And if the answer is yes, then we have an optimization question. So, of all of the possible routes, which one is the optimal route? Typically, optimal means the cheapest, the shortest, the fastest. We're trying to be efficient here. So, we are going to learn things about Euler circuit problems that will help us answer both of these questions. So, an Euler circuit means that every street or bridge or lane or highway in the area you're looking at has to be covered by the route. And we do have some more specific rules, like you want to cross each of those streets, bridges, whatever, exactly once. A circuit, you start and end at the same place. A path, you get from point A to point B, but we'll get into those details later. First, we want to start with some basic graph theory vocabulary. So, what are graphs? So, in general, a graph is not the x-axis, y-axis kind of graph that you're used to from algebra. A graph is a picture consisting of dots, which we call vertices. Vertices is the plural of vertex. and lines, which we call edges. The edges do not have to be straight lines, but they do have to connect to vertices. And if an edge connects a vertex to itself, it is called a loop. So let's take a look at a diagram and try to identify some of these features. Okay, so this is our graph. This is our diagram here. Our vertices are going to be all of these points, which are labeled A through F. Our edges connect vertices. So this edge we would call edge AB because it connects vertex A to vertex B. All right, so I'm going to actually highlight all of these so that I know when I have listed them. So I got AB. Let's start with all of the edges that start at A. So then I have AD as an edge. I have BB. That edge connects B to itself. BC. BE. Then I have two edges that connect C and D. And lastly, I have edge DE. Okay, those are all of my edges. I'm going to erase these scribbles so we can see our graph a little bit better. Now, in proper notation, we are not just going to list out the vertices and the edges. We are going to write the vertex set and the edge set. Remember that set means curly brackets. So our vertex set is going to be the set V, which is all of the vertices. And our edge set is going to be the set E. And then we just list out all of our edges that we listed in part B. All right, and knowing the vertex set and the edge set are enough for you to draw a graph. Now, we do have a couple more vocab words listed here that I did not specifically mention earlier. So we have an isolated vertex. That is vertex F. We call this an isolated vertex because it has no edges. Then the other thing we can look at is a multiple edge, which would be edge CD. We have multiple edges that connect vertex C to vertex D. And as we mentioned earlier, this is a loop because it connects B to itself. So those are the vocabulary words that we're going to start with for today. I do want to point out a couple more things about graphs. So basically, a graph defines a relationship between objects. So your objects are your vertices and your relationships are the edges. So if X is related to Y, then that means that there would have to be an edge from X to Y. Now, it does not matter how you draw the picture. It matters which vertices are connected to which other vertices. So A, B, C, D connected in a straight line is the same as if we fold it differently, because we still have A connected to B, connected to C, connected to D. A is connected to B, connected to C, connected to D. Because if we wrote out the vertex set and the edge set, they would be identical for these three diagrams. Our vertices are A, B, C, D, and our edges are A, B, B, C, and C, D. So you can see that a graph can be completely defined by its vertex set and its edge set. Let's look at one more problem. So going back to Koningsberg. Okay, one of Euler's most important contributions to graph theory is that you can take a situation, rewrite it or redraw it as a graph, and then you can apply all of the things in graph theory to that diagram to try to answer a question. So this whole idea is called modeling. You are taking a real life problem, translating it into math, doing the math, and then translating it back into context. So looking at the bridges of Koningsberg, here is a map of downtown Koningsberg. Okay. We have the different areas of the city. We have our 7 bridges, which are these little red lines. We want to know if it is possible to cross all 7 bridges exactly once. Okay, so let me show you how to turn this into a graph. All right, so we have 4 regions. We have A, which is the middle, L, which is our left bank, right, or R, which is our right bank, and D, which is this area. All right, then they are connected via the bridges. So this middle part is connected to the right bank here and here. The middle part is connected to the left bank here and here. The middle part is connected to area D through this bridge, and then D is connected to the right bank with this bridge and the left bank with this bridge. So we can redraw this and make it a little bit prettier. This is R, this is A, this is L, and this is D. We have multiple edges here between R and A, multiple edges between A and L, and then each of these regions are connected to D. So this would be our graph representing the bridges in the city of Koningsberg. And then we could apply some things that we will learn over the next few videos to this graph to answer the question of whether you can walk through the city of Koningsberg and cross all of the bridges exactly once. So that is it for today.